Welcome to the session on penalty function methods for evolutionary computation technique. In this particular session, we will be going through the introduction of the penalty function methods. Thereafter, we will discuss some of the methods such as static penalty, death penalty, dynamic penalty method, and so on. Thereafter, we will perform some hand calculations so that we will understand how this penalty function method works, and finally we will conclude this session. So let us start with the recap. In the previous session, we started with the constraint optimization formulation, in which our objective function was subjected to inequality constraint, equality constraints, and the variable bound. So for this particular problem or the constraint optimization problems, we have gone through the visualization of different types of spaces that will be made by the constraints. So we had continuous such a space, followed by we can have discontinuous such a space. We also have gone through the different types of constraint such as linear, nonlinear, as well as equality and inequality constraints. After that, we started with the optimality condition for unconstrained optimization, because that laid down the basis for finding the KKT condition or the optimality condition for constrained optimization. We used Taylor series function, Taylor series, to find the sufficient optimality condition for an unconstrained problem, which suggests that at a stationary point, say x bar, gradient of the function should be 0. Thereafter, we have gone through the sufficient condition. In this sufficient condition, we come up with the Hessian matrix, and as and when this Hessian matrix is positive definite, we say that the stationary point is a local minima for the function. Similarly, we also conclude about the maximization when the Hessian of the matrix is positive definite. If the matrix is not positive, not negative, then we have to say the point is a saddle point. Thereafter, we discussed about the method of multipliers. In that method of multipliers, we divided that section into two parts. First part was that we took an objective function with equality constraint. Since it was easy, we came up with the optimality condition via adding the Lagrangian multiplier or the multiplier with the constraint. So each constraint with Lagrangian multiplier was added into the objective function, and one unconstrained function was made. After finding the optimality condition with respect to the decision variable of the problem and with respect to the Lagrangian multiplier, we got the conditions. Similarly, when we took the objective function with respect to the inequality constraint, we first converted the inequality constraint into equality constraint with the help of slack variable, and then we followed the similar procedure. Finally, using the basis of method of multiplier, we came up with the KKT condition, which is referred as Karush-Kuntakar conditions. These conditions we have written for the one constraint optimization problem that involves both inequality as well as equality constraint. So apart from all those conditions, we also had complementary slackness conditions and the Lagrangian multiplier with respect to the inequality constraint should be greater than 0. In that particular KKT condition, we found that the point which is satisfying all the KKT conditions, it is a likely candidate for the optimum. However, if the point is not satisfying any of the KKT condition, we can always conclude that the point cannot be an optimal solution. Thereafter, we have gone through the necessary condition and the sufficient condition, and in that sufficient condition again the function should be convex, the inequality, active inequality constraints should be concave, and we should have linear equality constraint. For that particular point, if any point satisfying the KKT condition in that scenario, we can always say that a point is a local minimum. And the convexity of the function we defined with the help of a relationship, and also if we find the Hessian of the matrix at a given point, looking at the positive definite of the matrix, we can conclude whether the function is convex or not. So that mathematical understanding on the optimality of unconstrained as well as constrained optimization. Now we will discuss the penalty function method. So let us begin with the introduction here. So here we can see, first of all, we have to find why the constraint handling is needed with evolutionary computation technique. So as we can see that EC techniques are population based technique, meaning that we will be working with many of the points. In this case, you can see on the figure on the right hand side that we are using multiple solution or the points as we used in EC techniques. Now looking at this figure, we have box constraint based on x1 and x2. Similarly, we also have the constraint as you can see here. So because of this constraint, few solutions are feasible, which are represented by the green dots, and few solutions are infeasible, which are shown in the red dots. Now the question comes that if we are working on multiple points, how we can differentiate the feasible solution versus infeasible solutions. Therefore, we need some way to find out that who are feasible solutions and who are infeasible solution, and accordingly we should assign a fitness to those solution. So that's why we need constraint handling. Second important point is that we know that most of the practical optimization problem involve constraint. It can be one constraint or it can be multiple constraint. Since we want to solve those practical optimization problem, we want to know what is the optimum solution for that. So we need constraint handling techniques with EC techniques. So there are different types of constraint handling technique here. This is one of the good paper given by Professor Coelho. Although it is quite old, which was published in 2002, but this particular paper has covered most of the constraint handling techniques that can be used with EC techniques. So on the basis of that paper, we can have different kinds of constraint handling methods. For example, we can have penalty based methods, we can have special representation and operators so that we can find feasible solutions. Similarly, we can have separation of constraint and objectives, and finally we can also come up with the hybrid methods. So since there are various methods available, some methods we can use it directly into our formulation. So the objective here again is how we can find a fitness, and then how we can differentiate the feasible solution versus the infeasible solution. In this particular session, we will be focusing on penalty function methods. Now penalty function methods, these are found to be simple and most popular methods for handling the constraints. In these methods, if a solution violates any of the constraints, the solution is penalized by adding penalty with the objective function. So as the statement says that when a solution is infeasible, so we will try to find out that how much it is infeasible. So the term which we use is called constraint violation. So based on that constraint violation, we add penalty to the objective function. So suppose we are solving a minimization problem. In that case, we will be adding a penalty into the objective function value so that the infeasible solution will be penalized. On the other hand, if we are solving a maximization problem, we will be subtracting this penalty into the objective function method. So accordingly, we will use those penalty function method for minimization and for maximization types of problem. Now here, when we will be using penalty function method, all these methods, what they do is they convert the constraint optimization problem into the unconstrained optimization problem by adding this penalty term of each constraint violation to the objective function. And that is the whole purpose, that instead of solving the method as a constraint optimization problem, let us solve it as an unconstrained problem, because those unconstrained problem can be handled relatively easier when we are solving with the techniques which we have gone through now. So in this case, when we talk about the penalty function method, we have two types of penalty function methods here. First is called interior penalty methods. As we can see here, these methods work for feasible points and penalize points that are close to the constraint boundary. What this suggests that if the solution is feasible, then only we can use interior penalty method, and when all solutions are feasible, then we will be penalizing the solutions which are close to the boundary. So here the optimum solution will be somewhere inside the feasible search space, and that accordingly these method work. The another type of penalty method is exterior penalty method. Here these method penalize infeasible points but not the feasible solution, and that is an important statement. Why? Because the interior penalty method cannot handle any infeasible point. However, the exterior penalty methods can handle both feasible as well as infeasible. So whenever there is a feasible point, there will be no penalty at all, but if the solution is infeasible, then a penalty will be added to the objective function method, and that is the whole objective. Now if we look at the constraint optimization problem, so this is, we are familiar with this representation where we want to minimize our objective function. We have inequality constraint which is GJX, we have equality constraints, and we have variable bounds. Now from the definition of interior penalty methods and exterior penalty methods, we can see that EC techniques generally employ the external penalty methods. Why? Because as we refer to our first figure, when we are using multiple solutions, some solutions can be feasible and some solution can be infeasible. So in order to identify them, give a fitness to them, so we need a penalty function method. So for us, in EC computation techniques, we need exterior penalty methods. So as you can see in equation number 2, the penalty function method can be written as, this is the penalty function method based on the problem variable x, and we have a set of parameters or penalty parameters r. On the right hand side, we have function value, and as per the definition, we are adding a penalty term. So the omega is going to be the penalty term which we are adding. Looking at this representation, we can see this omega is a function of r, is also a function of inequality constraint and equality constraint. So all these constraints will be considered together. Now as we know that there could be multiple inequality and equality constraint, so r is representing a set of penalty parameters. As we know, omega is the penalty term that is chosen to favor the selection of feasible points over infeasible point, and that is the whole objective here, that we should penalize the infeasible solution more and we should not penalize the feasible solution, so that we can differentiate. So let us start with some of the exterior penalty methods here. So the first method that we use for equality constraint is called parabolic penalty. Looking at equation number 3, the omega can be written as in terms of r, and inside the bracket we have the equality constraint, and we are making a square. This square is important because when we have this equality constraint, means the left hand side equals to the right hand side, then whenever a point is infeasible, so the value of hx can be negative as well as positive. Here we are considering the minimization problem. So whatever be the penalty or a constraint violation we get it, we have to square them. So we are always adding a positive value with the objective function for minimization problem. So as we can see that this particular penalty method can handle only the equality constraint. Second thing is it can be used for the infeasible point. So we can say that it is an exterior penalty term, and we can very well use with EC techniques. In this particular case, generally we take a small value of r and we keep on increasing this value gradually. So initially when we start with a small value of r, so the solutions will be moving towards the close to the optimum solution without these constraints, and as and when we are increasing the value of this r, these solutions will be moving towards the optimum solution of constraint optimization problem. This is for the equality constraint. Now we have another method for inequality constraint. Here we can see we can have bracket operator here. This bracket operator in equation 4 can be seen as omega r times of, so we are using these two brackets, and inside it we have gx and we are making a square. So I'll show you the significance of a square afterwards. Let us see what we mean by this bracket operator. So if we say this bracket of alpha, this is going to be the exactly alpha when alpha is negative, meaning that if alpha is minus say 1.23, then bracket operator of alpha is also minus 1.23. Otherwise it is 0, meaning that whether if we are going to take say alpha is equals to 0.27, and if we find the bracket of alpha, then it is going to be 0 because it is a positive value. So here this particular bracket operator is complying with our representation. So as we know, these constraints in our formulation is written as gj of x equals to 0. So as and when the value of a g is equals to 0 or greater than 0, the solution is feasible, and as and when it is feasible, we don't have to apply any kind of a penalty. And when the solution is infeasible, this means that gj of x will take value smaller than 0. So we can very well fit this representation of gj of x greater than equals to 0 into this bracket operator. Now as you can see that in this equation number 4, the square is also multiplied. It's only because that since if the alpha is negative, it will give me the same value, and we are solving a minimization problem in which we want to add penalty into the objective function method. So the square term will make this negative value positive, and we will be adding this penalty into the objective function value. So here, as we know, as we can understood from the discussion, that we can handle the infeasible point with this penalty function method. So it is an exterior penalty term. In this case also, we start with a small value of r, and which we keep on increasing gradually with the iterations. And the important point about this method is it is one of the commonly used methods for handling inequality constraint. So with the help of these two types of exterior penalty methods, we will see the different kind of penalty function methods that are being used with EC techniques. So let us move forward with the representation of penalty function. As we can see in equation number 5, the penalty function method can be written as P of XR, the objective function. Now we are adding all the penalties with respect to the constraint violation of equality constraints, and then we are adding the penalty with respect to the constraint violation of inequality constraints. Now here, as we have mentioned, Rk and Rj are the penalty parameters for every constraint in our problem. So generally we keep beta is equals to 1 and gamma as 2. But from our previous discussion, we know that this gamma is going to be small. So either we take 1, so then in that case we have to take a mod, or we have to square the term of bracket operator. Now from the previous discussion, we can very well use the parabolic penalty for the equality constraint, but still handling equality constraint is always difficult. Why? Because it says that the left hand side should be equals to the right hand side. So having such point or satisfying such kind of equality constraint is always a challenging task for all optimization methods. So one of the way to handle the equality constraint is that we can convert this equality constraint into inequality constraint. So the point is, we can very well use the penalty function method for both equality and inequality. However, in order to suggest more efficiently the equality constraint, we can have a representation such as mod of hx minus epsilon should be smaller than 0, where this epsilon is the tolerance allowed. Generally, we keep a small value, say 10 to the power minus 3, minus 5, etc. So this particular new kind of a constraint for equality, it will make one equality constraint into two inequality constraints, and this inequality we can use it with our formulation, and we can very well use the bracket operator with such kind of inequality constraint. Now let us move with the types of penalty function methods. So there are various kinds, such as we can have death penalty, we can have static penalty, similarly the dynamic penalty functions, adaptive penalty, and there are some other approaches which are available in the literature, such as self-adaptive fitness formulation, stochastic ranking, etc. So the literature has so many penalty function based methods. Here we will be focusing on few of them. So let us start with death penalty function. Now the death penalty function, as you can see here on the right hand side, it says that infeasible solution is rejected and regenerated again. So point is that this death penalty method does not require or does not want any infeasible solution. So as and when any infeasible solution is generated, it is regenerated so that it will become feasible. Now let us look at the figure. So we can see that with EC techniques we work on multiple solutions, as you can see in the figure. Now when EC techniques is generating the green dots, as you can see, these green dots are feasible and death penalty can take care of these solutions. However, as and when there is a infeasible solution which is represented by the red color dots, then this penalty function will reject such kind of solution. So since we are not performing any kind of violation here, we can say that it is the easiest way to handle the constraint. Moreover, we are not looking at the penalized function, so we can say this is the computationally efficient in a way to handle with the feasible solution only. Moreover, it does not require to estimate the degree of violation for assigning the fitness to a solution. Now, it means that since the dynamic penalty method does not need any kind of infeasible solution or does not work on the infeasible solution, so all solutions for us are feasible. So, in that case we do not need any constraint violation, a particular method that will help us to differentiate the feasible and infeasible solution, and therefore, it will not calculate any kind of a constraint violation. It will accept if the point is feasible, it will reject the point if it is infeasible. Although this method looks simple, but there are certain limitations. So, let us see that. So, looking here, that if we look at this particular figure on the right hand side, now suppose we have a very small feasible region as it is shown in the shaded region, and again the green dots are the feasible points and the red dots are the infeasible point. So, when we want to use this death penalty, it is advisable for those problems in which the feasible space is limited. So, in that case, if we are going to solve a problem where the overall feasible search space is small, then it is not advisable to use such function. Looking at the figure on the right hand side, we can see that with the while using this death penalty, many of the solutions are infeasible. This means this method is going to reject all these infeasible solutions and will only take the feasible solution. So, as of now there are only 3 feasible solutions and rest of them are infeasible solution. So, which means that it can stagnate search of EC techniques for small feasible spaced problem. Why? Because we have less number of feasible solution as compared to the infeasible solution. There is another limitation as well here. Since we are rejecting the infeasible solution straightforward, here the point is there could be some scenarios where these infeasible solutions can be closer to the optimum as compared to the feasible solution. So, let us look a case on the right hand side. So, this for this particular problem, so it's the contours are drawn for a Himmelblau function and we have just one constraint as you can see here. Now, since EC techniques generated the random points in the plane of x1 and x2, we have the green dots as a feasible points and the red dots as a infeasible point. Say for the given problem, the optimum solution is shown here, which is in the blue color. Now, as compared to this optimum solution, we can see that the solution number 1, solution number 2, they are more closer to the optimum solution than the say solution number 3, and that is the disadvantage. Why? Because we are not able to exploit the infeasibility of the solution. So, basically looking at their constraint violation, if the constraint violation is small, our solution can be close to the optima or the boundary. Since we are rejecting those solutions and dealing with feasible solution only, then EC techniques may require more number of a generation or function evaluation to reach to an optimum. However, if we consider this infeasibility with the death penalty, we can very well exploit the area or the space near the optimum solution using feasible and infeasible solution, and EC technique can find this solution quickly. So, therefore, this is one of the limitation, that the infeasible solution can be closer to the optimum solution in the variable space than a feasible solution. The method cannot take advantage of such information as we discussed earlier. Now, the death penalty was not using any kind of penalty term. Now, we are coming to the static penalty, which will be using some penalty term to penalize the infeasible solution. So, if we look at the equation number 6, this is the same penalty function method we have written earlier, where we have the penalty function method written with the help of x and r, and on the right hand side we have objective function, then we have constraint violation with respect to equality constraint, and then we have constraint violation with respect to inequality constraint. So, using those constraint violations, we are making a penalty term here. So, why we call this is static? It is because the penalty parameters remain constant throughout the evolutionary process. So, when we have gone through the two types of penalty methods, that are parabolic as well as the bracket operator, in both the penalty function methods, we discuss that we start with the small value of r, and then we keep on increasing this particular value with the number of generation or iteration. But with a static penalty, we will always keep the value of r same. So, for example, rk value for kth constraint will remain the same throughout the generation. So, what could be the possible limitations of static penalty? Now, let us see that. Penalty function method, that is an important point, that the penalty function methods are problem dependent, meaning that depending on the problem, the penalty value, the value of r may be sufficient for a one particular problem, but may not be sufficient for other kind of a problem. So, as it is stated that if we take a small value of a penalty factors, then it may not be able to differentiate feasible and infeasible solution in the population. So, as we know that with the objective function, we are adding the penalty. Now, the value of r is itself small, then this penalty function method we cannot differentiate which is feasible and infeasible, and accordingly there will be not difference in the fitness assignment. However, if we take a large value, so if large value of a penalty factor can distort the penalty function, that can result in an artificial local optimum solution. So, that is another disadvantage, that if we keep the value of r say large, then in that case the contours of the penalty function method will distort, and because of that there could be some local or artificial optimas. So, let us look this particular case with an example given here. So, the figure on the left hand side, so again it is a Hamel-Blau function with just one constraint, and we have taken the value of r say 1. So, we are considering r1 is a small value. So, you can see that when the value of r equals to 1, we have such kind of contours. Now looking at the r value 10, the same penalty function method with the r equals to 10, you can see there is a change in the contours, and this change is with respect to just one constraint. Now, we can imagine a situation when we have many number of objective functions. We can imagine a situation when we have many number of constraints, and those constraints are added with the penalty parameters, and when we take a large value, the penalty function method will distort. So, the contours represents the distortion in the penalty function method, and therefore, if we take a small value, we cannot differentiate the feasible and infeasible. If we take a large value, then that will generate artificial optimas. Then in that case, our algorithm should be efficient enough to move towards the global optima rather than stuck in the local optima. Let us move to the another kind of penalty method, which is dynamic penalty. This dynamic penalty, as you can see here, that includes the current generation counter T. So, equation 7, we can see we have a penalty function method equals to the objective function, and we have included a term called C multiplied by T, and that everything power alpha. Now, here T will be representing the generation counter, and then rest of the term as we are writing for the equality and the inequality constraint. So, in this formulation, C, alpha, beta and gamma all are the user defined constants. Now, this particular equation 7 that suggests that if suppose the value of a T is 1, so basically the generation number 1, then this particular factor will be small. But as and when we will be moving towards the say generation number 10, 20, 30, this particular factor will increase. So, meaning that at the end of the iteration, if the solution is infeasible, we will be giving more penalty to the solution as compared to the solution at the beginning of the generation. Here, these two authors, they suggested to use a value of a C as 0.5, and as per our previous discussion, we can keep the value of a beta and a gamma. Here, the value suggested for alpha is 1. And now, in this particular discussion, we already did it, that the bracket operator is the Gj of x value remains the same when it is smaller than 0, otherwise it is 0, and equality constraint can be converted into an inequality constraint with this representation. What is the limitation of death penalty here? That although it is considered good for many EC techniques, it is difficult to produce good dynamic penalty factors for static functions. Why? Because the functions which we are using, especially the objective functions, objective function and constraints, we are considering them static. So, in that case, although it is performing good, but it is difficult to produce good dynamic penalty factors for those kind of functions. With this explanation, let us move to the adaptive penalty. Now, this adaptive penalty also uses the generation counter. So, as we can see, similar to the dynamic penalty, adaptive penalty also changes with the generation counter T. By these authors, they come up with the representation of adaptive penalty. Now, here we have the objective function plus lambda. So, this is the new term which they have added, and then we have the constraint violations, that is coming from the equality and inequality constraint. Now, here lambda is getting updated in every generation. So, this is how the lambda is taking care of the T, which is the number of or the counter on the generation, so that adaptively it will either increase or reduce the value. Let us look the alpha this lambda value. As we can see here, the lambda can be calculated as, so there is a case 1. For a case 1, we will be using 1 divided by beta and multiplied by lambda t. In case 2, we have beta 2 multiplied by lambda, and if there is no case from 1 and 2, we will be keeping the same value of lambda. So, let us understand what is case 1. Now, case 1 suggests that it denotes a situation where the best solution in the last k generation was always feasible. So, in this case, suppose we are running an EC technique and we have taken say k equals to 6. So, from the last 6 generation, if we have the best solution always a feasible solution, then in that case we will be using the case 1. Case 2 here denotes the situation where the best individual or a solution in the last k generation was never feasible, meaning that for some kind of a problem when we are using EC techniques, the problems are so difficult that we may not get the feasible solution at all. So if we consider say k equals to 6 generation, so from last 6 generation, if we find that the best solution was always infeasible, it was never be a feasible solution, in that case we use case number 2. Here beta 1 and a beta 2, both of them should be greater than 1 and beta 1 should be greater than beta 2. So let us understand more about this lambda term here. Now here what we can see in case 1, which says that our best solution was feasible for k number of a generation, meaning that we should reduce. So as you can see 1 by beta, since beta was greater than 1, so we are actually reducing the value of lambda t plus 1. In the other case, when the best solution is infeasible from the last k generation, so we have to increase this penalty, and therefore as per the case 2, we are multiplying beta 2 with lambda t for the next iteration. Otherwise, if there is a mix of population, meaning having feasible and infeasible, then we don't have to change the value of lambda. So as per our discussion, we can see here the term lambda plus 1 decreases if all the best solution in the last k generation are feasible. So this means we should reduce it. We have to increase the lambda t plus 1 if all solutions are infeasible. If there is a mix of feasible and infeasible solution, then we should not change this particular penalty. So what could be the limitation here? The major issue with this penalty is the setting of the parameters that can be difficult sometime. So the point is we have to take beta 1 and a beta 2. Now since beta 1 and a beta 2 should be greater than 1, the question is how much? Can we take 2, 2.5, 10? So setting those values for the problem is a difficult task, and that's why this is the limitation. So what are the major issues? If we look all these penalty function methods which we have gone through, what are the major issues? First major issue is choosing the best penalty term is not known a priori for any arbitrary problem, and that is difficult, since in every penalty function method we have to choose those parameters. So in that case, a parameter which may be sufficient for a problem 1 may be very large for problem 2 or very small for problem 3. So we have, if we are working on an arbitrary problem, in that case setting such kind of a value sometimes may not help to find an optimum solution for the constraint optimization. Second issue is the value. If we take a large value of the penalty term, that can distort the function with artificial optimum solution. So this case we discussed earlier. When we are taking a large value of r, it distorts the contour of the penalty function method. So those functions will be distorted, and if we have more number of constraint, the distortion will be up to the level that it can generate some artificial optimum solution. So in this case, if optimum solution is on the constraint boundary, then EC technique will push all the solution inside the feasible search space and may find difficult to move towards the boundary. So this is the case. Suppose we are starting with a very large value. So as compared to the feasible, infeasible solution will be penalized heavily. So since we are penalizing those solutions heavily, what will happen that this EC techniques will move or will take the solution in the feasible region. And suppose the optimum solution is on the boundary, which we have shown in one of the cases, then in that case the EC techniques has to further work so that these feasible solution will move towards the optimum solution. In case we take a small penalty term, then as we know that we will not be penalizing sufficiently the infeasible solution as compared to the feasible solution. So, in this way we are not able to differentiate which one is feasible, which one is infeasible, and our EC technique will be just wasting its effort towards searching in the infeasible space. So, therefore, whether we have to set a small value or a large value, and setting any value can be a large for a one problem, can be small for the another problem. So, these are always the issues with the penalty function methods. Now, with this introduction and understanding on the different types of penalty function method, let us perform some hand calculation. Here, for performing the hand calculations, we are using Hamel-Blau function. So, this Hamel-Blau function is a two variable function, and this is subjected to one constraint and constraint number 2. Here we are assuming that x1 and x2 both are greater than 0. Since the constraints are given as smaller than type, let us convert them in a greater than type. Why? Because it will fit into our generalized format of constraint optimization. So, what we can do here is we can multiply the constraint -1, or we can take the left hand term on the right hand side, and then every constraint will be of greater than type. So, by converting them, we have G1 and a G2, and you can see that both the constraints are converted into the greater than and equality type. Let us generate the solution in the range of 0 to 6 for both variable x1 and x2. So, let us take this table here. So, we have index, means we are considering 8 solutions, and their x1, x2 values are given in the column number 2. Consider a solution number 1. Now, this solution 1, x1 and x2 are given to us. As we know, if we fit this particular x1 and x2 value in our objective function, we get a value, say 364.823. Now, let us calculate the constraints. Why? Because we want to know which one is feasible or infeasible. So, in G1 we are again putting the value, we get plus 3.089. Similarly, if we put the value of x1 and x2 of solution 1, we get a value as 0.765. Now, as we can see, both are greater than 0. So, we can say that a solution 1 is a feasible solution because both the constraints are satisfied. If we take death penalty right now, so we will keep this solution because it is infeasible. Coming to the another kind of penalty functions method. So, let us see, well, let us take the same solution here. So, the function value which we have found in the previous slide. So, we are writing similarly the G1 value and G2 value at x1. Now, let us consider the static penalty. Now, since we know the formula here, we can directly fit the fx, and we have two constraints. So, we are writing this formula. So, here j is equals to 1 to 2 rj, and we have a bracket operator and a square here. Now, let us take r1 is 1 and r2 is 5. So, as you can see that r1 and r2 are user defined parameters. So, we have to start, or we have to choose those two parameters. Now, here the penalty function for x1 solution, you can find that it is given as the fx, and then r1 inside the bracket the g1 value, and then r2 inside the bracket we have g2 value. Now, since we know that if alpha is greater than or equals to 0, then alpha is going to be 0 when we use the bracket operator here, right. So, in that case we can see that both the constraints, the values, since both of them are feasible, so their values zeros we are having here. So, in this case the penalty function value is 364.823, which is the same as the objective function value. Let us take dynamic penalty now. In the dynamic penalty, we have objective function plus we have the factor which is changing with respect to the number of generation, and then we have a summation of inequality constraint. Since we have 2, so this should run for 2 only. Now considering c equals to 0.5 as we have found in the previous slide, alpha equals to 1, and let us assume that it is the generation number 1. Now in this case, if we fit these values here, so the penalty function, now there is no r here as you can see, and when we are putting the value here, so you can see that since g1 and g2 values are greater than 0, so we have taken 0 here. So the overall penalty term is 0, and we get the penalty function value same as the objective function value. So our observation here is, since the solution 1 is a feasible solution, the penalty function value remains the same for static and for dynamic penalty function method. So you can see here, these are the penalty function values which we get it from static and dynamic, and on the top we can see we have the function value. So that is good point, that if the solution is feasible, then we are not going to add any kind of penalty with the solution. Let us take a solution 2. So I will be discussing different kinds of situations or scenarios. So the scenario 1 was that the solution 1 was a feasible one. Now let us take a solution 2. In this solution 2, the objective function we calculate, it is coming out to be 692.216. We get a value of a g1. Now you can see that g1 value is minus 11.791, meaning the constraint is not satisfied. g2 is a plus value, means it is satisfied. Since g1 is not satisfied, we have to say the solution is infeasible. Since solution is infeasible, let us see how this penalty methods will change. Now let us consider the static penalty right now. We have penalty function given here, and we have the same formula as we have used earlier, taking r1 equals to 1, r2 is equals to 5. Let us put the value here. For the penalty function for a point 2, we can see the objective function, and inside the bracket operator, since r1 is 1, so we are writing directly the square, then we have 5 and then g2 value of a square. Now we know that this is feasible, so this is going to be 0 by the bracket operator. And since it is infeasible, so we are taking a square term and we are adding into the penalty into the objective function. So overall we can see that the penalty function value is more than the objective function value which is given on the top for an infeasible solution. Similar thing let us see with the dynamic penalty now. So the given the formula here, considering c 0.5, alpha 1, and let us assume we have first generation right now. So the penalty function value for a solution 2, we have function value now 0.5 into 1, and then we have a bracket operator for both the constraint. Since this is satisfied, it is going to be 0, and it is not satisfied, so we are taking a square term here, and finally we get a value as 761.726. Now here, since we consider the iteration or the generation number 1, suppose if we get the same situation in the 10th generation, then the same penalty dynamic penalty function value will become the objective function. Now you can see the change here, that 0.5 into 10. So this means that 5, and then we have the same values of the bracket operator square for g1 and a g2, and we get a penalty function value. Now if I compare this penalty function value with the with the penalty function value with t equals to 1. Now, what we can see here is that in the 10th generation, the penalty function value will be large. Also, if we compare with the static penalty, the term is quite large. So, this means that with the static penalty, whether it is generation 1 or a 10, the penalty function value will remain the same. However, with the dynamic penalty, as we have seen here, if it is generation number 1, then the penalty term will be less. However, when you consider penalty say 10th generation, the penalty term will be large, and accordingly the penalty function value will be so large. Let us take a third situation by considering the solution number 3 here. So, we are going to have solution 3. We calculate the objective function as given here. The G1 value is positive, but the G2 value is negative. Since G2 is not satisfied, so the solution is infeasible as per our definition. Let us find out the static penalty now. Now, the formulation is the same as we know. We are considering R1 is equals to 1 and R2 is equals to 5. By putting the value of x3 here, we have objective function value and then we have bracket operators. Now, we know that since it is satisfied, it is going to be 0, and here this constraint violation will be square and multiplied by 5. We are adding a penalty here. So, the overall penalty function value, we can see it is 289.320, which is larger as compared to the function value 269. For the given problem, let us have this dynamic penalty. In this case, using the formula given here and C 0.5 alpha 1, and for first generation, if we put all the values here, we can see that we have the objective function, we have the C into T, and then the bracket operator. We know this is going to be 0. So, the overall penalty function value is 271.133. Now, let us take the fourth case. Now, in this particular case, what you will see that the solution number 4, it has the objective function value, and look at the value of a G1, it is infeasible. Look at the value of a G2, this is also negative. Since both the constraints are negative, we will say that this particular solution is also infeasible. So, as of now, we have discussed 4 cases. First case is solution was feasible. Second case, G1 was not satisfied, so it is infeasible. Third case, G2 was not satisfied, that's why it was infeasible. And in the last case, both G1 and G2 are not satisfied, so that's why it is also an infeasible solution. So, let us find the penalty function value for solution number 4. Here, the static penalty using the same formula, taking the value of R1 equal to 1 and R2 equals to 0.5, by putting the value for a solution 4, we will get 614.671. Why? Because you can see that this particular term, so the constraint violation will be added, this is also added. So, both the constraint violation coming from G1 and a G2 are added and make a penalty for the given point. Looking at the dynamic penalty using the formula given here, taking C 0.5 alpha 0.1 and T equals to 1. If we put these values together, we will get, as you can see here, we have objective function 0.5 into 1, we have first constraint, we have second constraint. Since both of them are not satisfied, so their contribution will be added as a penalty, and we get the penalized function as 612.376. So, from these scenarios, you can see that we are adding only those, we are adding the penalty corresponding to the constraint violation. So, whether it is first constraint or second constraint or both of the constraint, when they are not satisfied, their constraint violation is added into the objective function, and we find the penalty function value for the given solution. So, let us look at the table now. So, here in this particular table, so the solution 1 was feasible. So, that is why the objective function value, static penalty function value and dynamic penalty function value are the same. In solution 2, G1 was infeasible. So, accordingly the penalty was added into the objective function and we got the two values, different values for static penalty and dynamic penalty. In the third case, G2 was infeasible, so that constraint violation was added and we get a static penalty function and in the dynamic penalty function values. In the case 4, both G1 and G2 were infeasible and accordingly we get our solution here. So, basically the fitness to a solution using static penalty and dynamic penalty function method. Similarly, if we follow the same procedure for solution 5 to 8, what you can see, the solution 5, since it is feasible, so the function value is the same as the static penalty function and dynamic. Similarly, for solution number 8. But solution number 6 and 7, the solution is infeasible. Therefore, the penalty term corresponding to their constraint violation are added into their objective function value. So, with this hand calculation, we can see that as and when the infeasible solution is there, we are penalizing that solution, adding the penalty corresponding to the constraint violation and the value of R1 and R2 accordingly. So, with this we have come to the closure of this particular session. So, what we have gone through in this, that what we found that these penalty function methods, they are commonly used for handling the constraint with EC techniques. In this way, when we are using this penalty function method, we can assign a fitness to a solution. So, generally the penalty term is added so that we will get smaller fitness for the feasible solution as compared to the infeasible solution. So, in that case we can differentiate, and you remember that this fitness can be used when we want to select any solution. And in this particular method, we assign penalty to the objective function when any constraint is not satisfied. In this particular class of penalty function method, we have gone through various different kinds of penalty function method, starting with the dynamic penalty, and then we have adaptive penalty function methods. So, as you can see that all these penalty function methods, they work differently, and therefore, the fitness value which we will get, especially for the infeasible solution, is different different from each other. And all these understanding the analysis of the penalty function method, mainly the static and the adaptive penalty, we consider dynamic penalty. So, we have taken the static and dynamic penalty function methods and we have taken a set of a solution. We performed the hand calculation so that we can understand how the solution is getting the fitness. With the explanation of these penalty function methods, I conclude this session. Thank you.